What if I told you that one of the most dominant teams in NASCAR history once made their engine physically grow bigger in the middle of a race? Not with some exotic technology, not with $1 million engineering program, but with something you could pick up at any grocery store for under $2. We're talking about wax. Plain, ordinary, everyday wax. And here's the thing, it worked so well for so long that when NASCAR finally caught on, the officials stood there scratching their heads because there was literally no evidence left. It had all burned away. Gone. Perfect crime. Almost. This is Engineera, and I spend way too much time thinking about the mechanical ingenuity, the borderline madness, and the absolute audacity that has defined motorsport history. If you're someone who loves digging into the hidden stories behind legendary racing moments, the cheating scandals, the mechanical wizardry, and the brilliant minds who pushed every possible boundary to find speed, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now, before we get into the wax, I need you to understand the world this story lives in. Because without the context, the trick sounds like a footnote. With it, it sounds like one of the most breathtaking acts of technical creativity the sport has ever seen. We're going back to the early 1980s. NASCAR's Winston Cup Series was not the polished, corporate, billion-dollar machine it is today. It was raw. It was loud. It smelled like burnt rubber and high-octane fuel and ambition. Teams worked out of small, often family-run shops. Budgets were tight. Rules were sometimes loosely written and even more loosely enforced. And in that environment, a certain kind of genius could thrive. The kind of genius that doesn't come from a university engineering program or a wind tunnel test. It comes from staring at a problem long enough that you start seeing solutions nobody else would even think to try. The rules in that era were clear on one thing: engine displacement. NASCAR mandated a maximum of 358 cubic inches for Winston Cup engines. Not 359. Not 360. 358. That limit was the law, and the inspection process was the enforcer. Before qualifying, officials would check every engine using a pump that measured cylinder volume. They'd rotate the crankshaft to bottom dead center, inject fluid into each cylinder, and measure exactly how much it held. Add all 8 cylinders together, and you had your displacement figure. Pass the limit, you race. Exceed it, you go home. Simple, brutal, and supposedly airtight. Here's what most people don't realize, though. That inspection happened with a cold engine. The officials would roll up to a car that hadn't been started yet, run their measurements, write down their numbers, and move on. Once you passed tech, that engine was considered legal for the entire race weekend. Nobody was going to open it up again post-race unless something egregious happened. And that assumption, that cold equals permanent, that what you measure before the race is what you get during it, was the crack in the system that Maurice Petty found. Maurice Petty. If you don't know that name, you should. He was the engine builder for Petty Enterprises, the most storied team in NASCAR history. His brother was Richard Petty, the king, the 7-time champion, the man with 200 career wins and an iconic STP paint scheme that became synonymous with American motorsport. But behind every great driver, there's a great engine builder. And Maurice was more than great. He was obsessive. He was inventive. He was the kind of guy who would pull apart an engine after midnight just because something sounded slightly different than it should. He thought about horsepower the way poets think about words. Every cubic inch mattered. Every revolution per minute was precious. Look, here's the honest reality of what teams were dealing with in that era. Junior Johnson's operation seemed to have found extra power somewhere. Other top teams were mysteriously pulling away in the late stages of races. The technology arms race was real, and Petty Enterprises was not about to get left behind. Maurice had already tried the usual routes: aggressive camshaft profiles, exotic fuel additives, careful attention to port work and combustion chamber design. But the displacement ceiling was always there, this hard mathematical wall beyond which nobody was supposed to go. And then one day, he was working in the shop, and he noticed something about paraffin wax. Specifically, he noticed the way it behaved with temperature. At room temperature, wax is solid, rigid, taking up definite space. Heat it up to around 140 degrees Fahrenheit, which is not particularly hot by engine standards, and it transforms completely. It melts into a liquid that flows freely, takes up less defined space, and leaves virtually no residue when it burns away through an exhaust system. Now you might be thinking, okay, so what? Lots of materials melt. What does that have to do with engine displacement? Everything. Absolutely everything. Here's the idea in its purest form. Fill the combustion chambers with precisely measured amounts of wax before inspection. The solid wax occupies volume inside the cylinders, effectively reducing the measured space. When officials pump in their measurement fluid, they're reading a number that includes that displaced wax, so the engine checks in at a legal 358 cubic inches. Then the race starts. The engine fires up, temperatures climb rapidly, and within 10 to 15 laps, somewhere between 200 and 400 degrees Fahrenheit in those combustion chambers, the wax is long gone. Melted into liquid, pushed out through the exhaust system in microscopic droplets, completely combusted and dispersed. And those chambers are now bigger. Measurably, meaningfully bigger. The engine has just grown from 358 cubic inches to approximately 373 cubic inches while running at full speed around a racetrack at 200 miles per hour. 15 extra cubic inches. In everyday terms, that sounds like nothing. In NASCAR, using the industry standard calculation of roughly 2 horsepower per cubic inch at peak output, that's 25 to 30 additional horsepower appearing out of nowhere in the middle of a race. To put that in perspective, the difference between a competitive mid-pack car and a race winner in that era could be as little as 15 to 20 horsepower. So we're talking about an advantage that was, by the standards of the time, enormous. It was the mechanical equivalent of carrying a secret weapon in your back pocket that nobody could see, detect, or prove. The preparation required for this to work was extraordinarily precise. Maurice couldn't just stuff random amounts of wax in and hope for the best. Each cylinder needed an exact, carefully calculated amount. Too much wax and the engine would fail inspection, immediately disqualifying the car before a single lap was run. Too little and the power gain would be negligible, not worth the risk. They had to account for the unique geometry of each combustion chamber, the valve pockets, the spark plug recesses, the specific contours of the piston crown. Every variable had to be calculated and controlled. The type of wax mattered enormously, too. Standard candle wax was out of the question. It would leave behind carbonaceous deposits that could foul spark plugs, contaminate oil, and potentially damage valve seats. What they needed was a high-grade paraffin with a melting point precisely in that range, high enough to stay perfectly solid during inspection and initial startup, low enough to liquefy completely within the first 15 laps. After extensive secret testing in their Level Cross, North Carolina facility, they identified the right material. Clean, complete combustion. No residue. No evidence. The kind of careful material science that most people would associate with aerospace programs, not a NASCAR garage. Installing the wax was itself a skilled process. They would gently warm it to the point of pliability, press it carefully into the combustion chambers, ensuring perfect contact with every surface and absolutely no air pockets. Air pockets would create inconsistent measurement results during inspection. Then they would let it cool and harden completely before assembly. The whole preparation process added hours to the build time, but every minute was worth it if the plan held together. The testing phase was where Maurice's true engineering discipline showed itself. They couldn't test this at any public facility. No press allowed, no rival teams watching. They built a dedicated dynamometer cell at the Petty shop specifically designed to simulate the full thermal cycle of a race. They would run these engines for hours, watching the power curve change in real time as the wax melted. The data they collected was fascinating and validated everything the theory predicted. At startup, the engine with its wax-reduced displacement would produce around 615 to 620 horsepower. Normal, unexceptional, nothing to raise eyebrows. By lap 5 of a simulated race, with temperatures climbing, the wax beginning to soften, they were seeing 630. By lap 10, as the wax moved toward full liquefaction, 640. By lap 15, with the chambers clear and the engine running its true displacement, a steady 650 horsepower with a torque curve that was noticeably fatter throughout the RPM range. The engine pulled harder coming off corners. It breathed better at high speed. It simply had more of everything that makes a racing engine fast. And here is where it gets really interesting. Because the power gain wasn't just about peak horsepower. Adding displacement fattens the entire torque curve, which means more grunt across a broader RPM range. Richard Petty could use different driving techniques, different line choices, different braking points, because he had reserve power his competitors simply didn't have. He could be gentler on the throttle early in corners and still accelerate harder out of them. He could draft differently, pass differently, manage tire wear differently. The wax wasn't just giving him more power. It was giving him a fundamentally different and superior machine to drive. The 1983 season opened with the Daytona 500 in February, and Petty Enterprises arrived with quiet confidence. The kind of confidence that comes not just from preparation, but from knowing something nobody else knows. Richard Petty qualified respectably, nothing suspicious, nothing that would draw extra scrutiny. The car looked right. The engine sounded right. The numbers on the inspection sheet looked exactly right. Because they were. Cold, with the wax packed into those combustion chambers with surgical precision, that motor was measuring exactly 358 cubic inches. Legal as a library card. Then came February 20th, 1983. The Miller High Life 500 at Richmond Fairgrounds Raceway. A 1-mile oval, tight and demanding, the kind of track where engine torque matters as much as peak horsepower. Richard Petty in the famous number 43 STP Pontiac absolutely dominated the field. He led 207 of 400 laps. Not just one, dominated. The kind of dominant performance that makes other crew chiefs walk back to their haulers and stare at their data with confusion written all over their faces. Their cars were not slow. Their engines were legal. So why was the 43 pulling away like it had a completely different power plant under the hood? Because it did. Approximately 15 laps into the race, somewhere around lap 10 to 15, if Maurice's dyno data was accurate, that Pontiac engine had quietly, invisibly, completely legally, by the measurement standards of the moment, grown from 358 cubic inches to 373. Richard Petty wasn't just driving a good car. He was driving a fundamentally different category of machine than everyone else on that racetrack, and nobody knew it except the people who built it. The post-race inspection was routine. NASCAR officials checked weight, ride height, body templates, the standard checklist. The engine was not pulled. It was not measured. Why would it be? The car had passed pre-race tech without a single flag. The King had won his 198th career victory, and the crowd had gone home happy. Another Saturday night in NASCAR? Nothing to see here. Except there was something to see. A sharp-eyed NASCAR technical official named Dick Beatty had been watching the 43 car throughout the race. Not specifically looking for the engine trick, because nobody was looking for that. Nobody had even conceived of that possibility yet. But Beatty noticed something about the left side tires. They looked slightly oversized, just a fraction of an inch too large for what was supposed to be mounted on that car. Now, in isolation, that kind of tire discrepancy was almost trivially minor. 1/10 of a second per lap at most. Teams played with tire sizes all the time in that era, pushing the edges of what the rulebook permitted. But Beatty was the kind of official who believed that if a team was cheating on the small stuff, they were probably cheating on bigger stuff too. That tire observation was the thread. And when you pull the right thread, the whole sweater comes apart. NASCAR initiated a deeper inspection. Not the usual checklist items, but a full teardown. They pulled the engine, brought in precise measurement equipment, and began working through every component. Bore and stroke were measured with micrometer accuracy. Connecting rod lengths were checked. Compression height of the pistons was verified. And when they assembled all those measurements and ran the displacement calculation, the number that came back was not 358 cubic inches. It was 373. The room went quiet, then very loud. Maurice Petty's initial response was exactly what you'd expect from someone who had been preparing for this moment and hoping it would never come. He suggested measurement error. He proposed that the engine might have sustained damage during the race that affected its dimensions. He offered alternative explanations with the calm, measured delivery of a man who had thought through every possible defense. But NASCAR kept digging. They brought in a borescope, a thin optical instrument that allows you to see inside cylinder bores and combustion chambers without full disassembly. And in the valve pockets of those combustion chambers, they found something. Not much, just traces. Microscopic droplets of a waxy substance that had not quite made it out through the exhaust system during the race. Almost nothing. But almost nothing was enough. Now, you might be thinking, how can you prove what that substance was, or where it came from? And that's actually a fair question. NASCAR's case was largely circumstantial. They had an oversized engine and trace material that looked suspicious, but they couldn't reconstruct the entire trick from what was left behind. What they could prove was that the engine exceeded the legal displacement limit. The how was educated inference. The what was irrefutable mathematics. Bill France Jr. himself flew down to deal with the situation. This was not a call you delegated to a regional official when the team involved was Petty Enterprises. Richard Petty was NASCAR's most beloved figure, the sports ambassador, the face on the promotional posters and the voice in the television commercials. You didn't handle the Petty family like you handled some underfunded independent team from the back of the grid. But you also couldn't look the other way, because if word got out that NASCAR had found an illegal engine on the most famous car in the sport and done nothing, the credibility of the entire competition structure would collapse overnight. The penalty handed down was significant by the standards of the era. Petty Enterprises was fined $35,000, which translates to approximately $100,000 in today's money. Richard Petty was docked 104 championship points, a meaningful blow in a title fight where margins between positions could be razor thin. Maurice Petty was suspended as crew chief for the remainder of the Richmond proceedings and the subsequent race at North Wilkesboro. Critically, and this is the part that stung most, Richard kept the win. The victory stood in the record books. His 198th career triumph remained official. But everything around it was tainted. The reaction across the NASCAR garage was immediate and complicated. Anger from some quarters. Grudging admiration from others. Junior Johnson, who was himself a legendary practitioner of creative rule interpretation, having famously perfected the art of drafting at Daytona before most people understood what drafting was, reportedly said that he knew something was different about the Petty motors. He said his team had torn apart their own engines looking for whatever advantage the 43 car seemed to have. They never found it because they were searching for mechanical solutions, modified components, trick machining, exotic materials in the traditional sense. It never occurred to anyone to look for something that wouldn't be there anymore by the time the race ended. That's the true brilliance of the wax trick when you examine it carefully. It wasn't just clever chemistry. It was clever forensics. Maurice Petty had designed a scheme where the evidence destroyed itself. The crime scene cleaned itself up. By the time any investigation could begin, the perpetrator had already fled through the exhaust pipe in a cloud of invisible vapor. If Beatty hadn't spotted those tires, if NASCAR hadn't decided to do a full teardown for unrelated reasons, the engine would have passed any post-race inspection perfectly. 358 cubic inches. Cold, measured, verified. Legal as the day it was built. The physics of why this works so elegantly deserve a closer look, because understanding the mechanism deepens the appreciation for how carefully it was designed. Engine displacement, as we established, is the total volume swept by the pistons. It's determined by bore diameter and stroke length, both of which are fixed mechanical dimensions that don't change during a race. What Maurice exploited was not those dimensions but the combustion chamber volume above the piston at top dead center. By filling that space with wax, he effectively made the cylinder appear smaller than it was when measured using the fluid injection method. The fluid couldn't fully occupy the chamber because the wax was already there. Remove the wax, and the true volume was revealed. The genius move within the genius move was selecting a melting point that aligned perfectly with engine operating temperatures. A normal NASCAR engine of that era would see coolant temperatures of around 180 to 200 degrees Fahrenheit, and combustion chamber surface temperatures significantly higher, often exceeding 300 degrees Fahrenheit within the first few laps of racing. At 140 degrees Fahrenheit melting point, that wax was gone long before the engine reached full operating temperature. By the time Richard Petty was running at race pace, the transformation was complete. The engine was fully awake, fully grown, fully illegal, and completely undetectable without a teardown. The camshaft profile in that engine was also part of the deception architecture. Maurice had ground a cam that was specifically designed to work optimally at 373 cubic inches. At 358, the engine would run well enough to pass muster during warm-up and early inspection laps, but it wasn't living up to its potential. Once the displacement increased, the cam timing came into its proper range. The intake and exhaust events that had seemed slightly aggressive for the smaller configuration were suddenly perfectly matched to the bigger engine. It was like a turbocharger that didn't need boost pressure to work, just heat and time. The carburetor jetting told a similar story. It was set slightly rich for a 358 cubic inch application, which would normally be seen as a minor tuning imperfection. But for a 373 cubic inch engine running at full chat, that jetting was spot on. The fuel delivery matched the airflow requirements precisely. Ignition timing was set conservatively enough to prevent detonation at either displacement configuration, threading the needle between two different engine realities within a single set of fixed components. What Maurice Petty built was not just a cheating device. It was a system. Every component of that engine was designed to function within two different operational states: the cold inspection state and the hot race state. The transition between those states was managed entirely by ambient thermodynamics. No switches, no driver inputs, no crew intervention. The physics did the work automatically and invisibly. Other teams in that era were doing their own creative engineering, to be clear. The 1980s NASCAR garage was not a place of innocent compliance. Teams were experimenting with body panels acid-dipped to save weight, hydraulic systems that could alter ride height during a race, fuel additives that pushed the boundaries of what the rulebook permitted, and tire compounds that were technically legal but functionally different from what competitors were running. The wax engine existed in a culture of aggressive rule interpretation where the written regulation was the floor, not the ceiling, of what teams were willing to attempt. But even within that culture, the wax trick stood apart. Because it wasn't just bending a rule. It was exploiting a fundamental assumption in the inspection process itself. NASCAR assumed that a cold measurement was a permanent measurement. Maurice Petty proved that assumption wrong in the most elegant way possible, using nothing more than basic thermodynamics and a material you could find in any hardware store. That's not just cheating. That's engineering philosophy. That's lateral thinking applied to competition at its most ruthless. The immediate aftermath of the Richmond scandal forced NASCAR into an uncomfortable position. They had caught the most famous team in the sport running an illegal engine, but the evidence of exactly how that engine had been made illegal was largely gone. What remained was a displacement number that didn't match the rulebook and traces of a suspicious waxy substance that pointed toward a method without definitively proving one. NASCAR did what regulatory bodies always do when they realize their system has been outsmarted. They rewrote the rules. Not just the specific rule that had been exploited, but the entire framework around engine inspection. The changes came quickly, and they were comprehensive. Random post-race engine displacement checks became standard procedure. Not every car, every race, but enough that teams could never be certain their engine wouldn't be measured after the checkered flag. More importantly, NASCAR began developing procedures for hot displacement checks, measurements taken after the engine had been run to operating temperature. This single change made the wax trick permanently impossible. If officials could measure displacement with a hot engine, any wax would already be gone, and the true cubic inch figure would be right there in black and white. The specific vulnerability that Maurice had identified and exploited was sealed shut within months of Richmond. But the changes went further than just displacement measurement. NASCAR hired additional technical officials, invested in more sophisticated measurement equipment, and began requiring detailed documentation of every inspection at every event. A paper trail was created where previously there had been handshakes and assumptions. The romantic era of two guys and a dial gauge deciding whether a motor was legal was giving way to something more institutional, more rigorous, and significantly less exploitable by creative minds working outside the boundaries of conventional thinking. Here's what most people don't realize about the regulatory response to incidents like this. The rule changes didn't just affect the specific trick that was caught. They changed the entire culture of technical inspection across the sport. Officials who had previously approached their jobs with a certain comfortable routine began looking at everything differently. If a team could hide an extra 15 cubic inches using wax, what else might they be hiding using principles that hadn't been thought of yet? The paranoia was productive. NASCAR's technical department became sharper, more questioning, more willing to dig beyond the surface of what a car presented during inspection. Other teams and engine builders watched all of this with intense interest. The engineering community in NASCAR is small and interconnected. People move between teams, share information at the racetrack, talk to each other in the garages during rain delays. Word of what Maurice had done spread quickly through that community, even if the specific details remained murky for years. And the immediate reaction from other engine builders was not moral outrage. It was professional respect mixed with competitive evaluation. Could something similar work in a different form? Were there other materials with useful properties? Were there other inspection assumptions that could be similarly exploited? Some teams reportedly experimented with dry ice, which offered the theoretical advantage of simply sublimating from solid to gas without leaving any liquid residue at all. The problem was that dry ice at -109°F would cause thermal shock to precision-machined aluminum components, potentially cracking cylinder heads or warping combustion chamber surfaces. The material science didn't cooperate. Others thought about liquid nitrogen, which offered even more extreme temperature characteristics, but presented even more severe problems with thermal management and component integrity. The wax worked because it was benign. It didn't damage anything on its way out. Alternative materials that melted or sublimated at lower temperatures tended to be either too destructive or too volatile to handle safely in a racing environment. What this period of experimentation revealed was that Maurice Petty hadn't just stumbled onto a lucky trick. He had found, through careful systematic testing, the specific material in the specific temperature range that made the scheme physically viable. Paraffin wax with a melting point around 140°F was not an obvious choice. It was the right choice. And identifying the right choice out of all the possible options required genuine scientific thinking, the kind of methodical approach to problem solving that would be recognized as rigorous engineering in any other context. Let's talk about the financial dimension of this, because it's often overlooked when people discuss the Richmond scandal. The $35,000 fine sounds punitive, and by 1983 standards it was substantial. But consider the full economic picture. Prize money for winning a Winston Cup race in that era ranged from $30,000 to $60,000 depending on the event and the specific purse structure. Sponsorship bonuses for wins were often equal to or greater than the prize money itself. A team winning 10 races in a season, with even half of those potentially aided by the wax trick, could be looking at hundreds of thousands of dollars in additional revenue compared to a team finishing consistently in the top 5 but not winning. The cost-benefit calculation was not obviously wrong. The fine was painful, the points penalty was meaningful, but the wins generated revenue that likely exceeded the penalty by a significant margin. And this was before you factor in the competitive positioning value of being seen as a winning team, which attracts better sponsorship deals, better driver talent, and better supplier relationships in subsequent seasons. Cheating that works is an investment with a return. The risk is the return is clawed back when you get caught. But if the scheme runs for multiple seasons before detection, the economics can still favor the gamble. This brings up a question that serious historians of the sport have debated for decades. How long did the wax trick actually work before Richmond? Maurice Petty never fully admitted to the scheme, let alone provided a timeline of when it began. Richard Petty maintained throughout his career that he drove what Maurice built and trusted his brother's judgment completely, which is a beautifully crafted statement that manages to say nothing specific while acknowledging everything generally. The official record shows a dominant period for Petty Enterprises in the early 1980s that coincides with when the trick might have been in use. But correlation is not causation, and the Petty operation was formidable by any measure. What we can say with reasonable confidence is that the scheme was sophisticated enough that it didn't emerge fully formed overnight. The precision of the wax installation, the careful material selection, the camshaft and carburetor tuning designed to work across 2 displacement states, the dedicated dyno testing program, all of this suggests months of development work before the first race application. You don't develop that level of operational procedure in a weekend. This was a program, not an experiment, and programs take time to build and refine. The human stories around the scheme are as compelling as the technical ones. Think about the crew members who knew. In a racing team of that era, the engine department was typically 3 to 5 people at most. Everyone working on that motor would have known what they were doing during the build process. The wax installation was too visible, too deliberate, too carefully measured to be something only Maurice knew about. These were people carrying a significant secret in a sport where everyone talks constantly, where rivals were always looking for information, where a single overheard conversation in a garage could unravel everything. The pressure on those individuals must have been extraordinary. Every race weekend, watching NASCAR officials run their pre-race inspection, knowing exactly what those officials weren't finding, waiting for the moment when someone looked a little too closely or asked a slightly different question. Then watching the race unfold, knowing that somewhere around lap 10 to 15, the engine was changing, growing, becoming something different than what had been inspected and approved. And then the relief of the checkered flag, the victory lane celebration if it came, and the quiet knowledge that the evidence was already gone. Smokey Yunick, NASCAR's legendary master of creative engineering, commented on the wax trick in interviews years after the Richmond incident. Yunick had built his entire reputation on finding solutions that were technically legal while being practically advantageous in ways the rulebook writers hadn't anticipated. His Daytona shop was famous for cars that met every written specification while somehow being faster than anything else on the track. When he heard the details of what Maurice Petty had done, his reaction was characteristically direct. He said it was one of the cleverest things he'd ever heard of in racing. Not the execution, though the execution was impressive. The concept. The idea of using the inspection process's own assumptions against it. Yunick understood intuitively that the most elegant cheating doesn't fight the rules. It uses the rules' blind spots against themselves. That insight points toward something important about the nature of competitive engineering in motorsport. Rules are written by humans, and humans make assumptions. They assume that what they measure stays constant. They assume that materials behave predictably. They assume that the physics of inspection are the same as the physics of racing. Maurice Petty found a place where those assumptions broke down, and he built a program around exploiting that breakdown. That's not fundamentally different from what legitimate engineering does. Legitimate engineering also finds places where conventional assumptions break down and exploits those breakdowns to achieve better outcomes. The only difference is which side of the rulebook you're working on. The international motorsport community was paying attention to all of this as well. Formula One, which was simultaneously developing its own extraordinarily complex technical regulations in the early 1980s, watched the NASCAR wax story with interest. The F1 technical culture was already deeply familiar with the concept of cars that were one thing at inspection and another thing on track. Active suspension systems that would lower the car at speed, water-cooled brake systems that were technically legal as declared ballast but served primarily as adjustable weight, turbocharger boost systems with elaborate management schemes that could mask their true output during scrutineering. The wax trick, simple as it was by F1 standards, resonated with engineers who understood the philosophical principle at work. Sports car racing had its own version of this conversation. In endurance racing, where engines ran for 24 hours and were sealed between inspection periods, the question of what happens to a motor over time had always been present. Teams had long known that engines tend to grow slightly as they wear in during a race, as components reach thermal equilibrium and tolerances settle into their operating state. The wax trick took that natural phenomenon and amplified it deliberately and dramatically. What was an unintentional fraction of a cubic inch in a legitimate engine became a deliberate 15 cubic inch transformation in Maurice's design. The technical education value of this story has only grown with time. Today, engineering programs that teach design thinking and lateral problem-solving use case studies from sports and competition to illustrate how constraints can be reframed as opportunities. The wax engine is a perfect example of constraint reframing. The constraint was the 358 cubic inch limit enforced by cold measurement. Maurice reframed the constraint by asking not whether he could build a bigger engine, but whether he could build an engine that was measurably small when cold and effectively large when hot. The constraint didn't change. The question being asked about the constraint changed completely. That intellectual move, reframing the question rather than attacking the problem directly, is the foundation of some of the most significant engineering advances in history. The Wright brothers didn't ask how to make a more powerful engine. They asked how to make a structure that could fly with the power available. Apple didn't ask how to make a better computer. They asked what a computer should feel like to use. Maurice Petty didn't ask how to make a legal 358 cubic inch engine more powerful. He asked how to make an engine that would be 358 cubic inches during inspection and 373 cubic inches during the race. Same problem, completely different question, completely different solution space. The legacy of the wax engine trick extends far beyond the Richmond penalty and the rule changes that followed. To truly appreciate what Maurice Petty accomplished, you need to understand what happened to NASCAR's technical landscape in the years immediately after 1983, because the ripple effects of that one incident reshaped the sport's competitive culture in ways that are still visible today. The Richmond scandal was not just a story about one team getting caught. It was the moment NASCAR realized that its inspection process was built on assumptions rather than verification, and that assumption-based regulation in a sport full of brilliant, competitive, highly motivated engineers was a structural vulnerability waiting to be exploited by anyone clever enough to find it. The technical department expansion that followed was significant. NASCAR went from a relatively lean inspection staff to a more robust operation with specialized roles and defined procedures for each category of measurement. Engine inspection became its own discipline within the technical department, staffed by people with genuine mechanical engineering backgrounds, rather than experienced mechanics who had moved into official roles. The difference matters. A mechanic knows how engines work. An engineer knows how engines can be made to work differently than intended. You need the second type of mind to catch the second type of thinking. Equipment investment followed the staffing changes. The fluid pump displacement measurement method that the wax trick had exploited was supplemented with additional verification techniques. Bore measurements with precision gauges, stroke verification through direct mechanical measurement, compression ratio checking that could cross-reference displacement figures against combustion chamber volume data independently. No single measurement method could be fooled in isolation anymore. You would have to fool multiple independent verification systems simultaneously, each using different physical principles, to achieve what Maurice had achieved with a single cold measurement blind spot. Here's the thing about this escalation pattern. It's not unique to NASCAR. It appears in every regulated competition where the stakes are high enough to motivate serious technical creativity. Formula One has gone through multiple cycles of this exact dynamic. A team finds a loophole, exploits it successfully for a period, gets caught or the rule gets clarified, and the regulatory framework becomes more sophisticated as a result. The FIA's technical regulations grew from a relatively straightforward document in the 1950s to a document of extraordinary complexity today. And every paragraph of that complexity traces back to something a team did that the original, simpler rules didn't anticipate. The rules are written in the language of previous violations. In NASCAR's case, the post-Richmond regulatory evolution had an interesting secondary effect. As inspection became more rigorous and creative, mechanical trickery became harder to execute. The competitive advantages available to teams shifted toward areas that were harder to regulate. Aerodynamics, which NASCAR's rules addressed but couldn't fully control given the inspection methods available in that era, became increasingly important. Setup philosophy, the complex interplay of suspension geometry and tire behavior and chassis balance, became a deeper differentiator, and the quality of the driver himself became more decisive when the mechanical advantages were more tightly constrained. Richard Petty's career trajectory after 1983 is instructive in this context. He would win his 200th career victory in 1984 at Daytona, a win that was itself surrounded by controversy over the engine configuration in that car. But after 1984, wins became increasingly scarce. The king who had dominated the 1970s and early 1980s went from being a consistent race winner to a respected but no longer dominant competitor. Multiple factors contributed to this, including the natural progression of age and the increasing competitiveness of younger drivers with better funded operations. But it's difficult to ignore the timing. The period of Petty Enterprises' greatest dominance coincided with the period when their most creative technical innovations were available and undetected. Now, you might be thinking that this narrative unfairly implies Richard Petty's success was primarily a product of cheating rather than genuine skill. That would be a misreading of the situation. Richard Petty was an extraordinarily talented racing driver by any objective measure. His car control, his racecraft, his ability to manage tire wear over long distances, his instinct for positioning and timing during restarts, these were real skills that no amount of extra cubic inches could manufacture. The wax engine gave him an advantage. His talent converted that advantage into victories. Both things can be true simultaneously. What the wax engine story actually reveals about Richard Petty is perhaps more interesting than the cheating angle. It reveals the competitive culture he came from and operated within. The Petty family approach to racing was total. They built their own engines, fabricated their own chassis components, developed their own setup philosophies, and pushed every technical boundary they could find. Winning was not just the goal. It was the standard against which every decision was evaluated. If Maurice had found a way to extract more power from the engine, Richard's job was to take that power and turn it into victory lane appearances. The division of labor was clear, and both sides of it were executed at the highest level. The broader NASCAR garage culture of that era deserves more examination because the wax trick didn't emerge from a vacuum. It emerged from a specific competitive environment where the boundary between innovation and violation was deliberately blurry, and teams routinely operated in that gray zone. Junior Johnson, who we've mentioned several times, built his entire competitive philosophy around finding things the rulebook didn't explicitly prohibit. His famous observation that it isn't against the rules if the rules don't say you can't do it was not cynicism. It was a genuine engineering philosophy about the relationship between written regulation and competitive practice. Holman Moody, The legendary Ford racing operation of the 1960s and early 1970s had operated by similar principles. Their engines were masterpieces of finding power in places the rules hadn't specifically addressed. Their chassis work pushed the boundaries of what was technically legal in ways that inspectors often couldn't definitively characterize as violations. The creative culture that produced the wax trick was decades in the making, a tradition of competitive ingenuity that treated the rulebook as a starting point for creative thinking, rather than a ceiling on what was permissible. This is where it gets really interesting, because when you examine the wax trick through this cultural lens, it looks less like an aberration and more like the logical endpoint of a philosophy that had been developing in NASCAR for 30 years. The sport had always rewarded teams that found speed in unexpected places. The difference in 1983 was that Maurice Petty found speed in a place that was unambiguously outside the rules rather than in the gray zone the sport had always tolerated. The line between creative engineering and cheating had been crossed, clearly and provably. But the spirit that drove him across that line was the same spirit that had driven NASCAR's greatest technical innovations throughout its history. The material science angle of the wax story has attracted serious attention from engineers who came to it years later. The specific properties of paraffin wax that made it useful for this application, its sharp melting point, its complete combustion characteristics, its low viscosity when liquid, its chemical inertness relative to engine components, represent a surprisingly sophisticated material selection problem. Modern engineers who have analyzed the scheme note that selecting paraffin over other wax types or similar materials required understanding several competing physical requirements simultaneously. The material had to be solid at ambient temperature, liquid at engine operating temperature, combustible without residue, and non-reactive with aluminum, steel, and cast iron engine components. That's not a trivial list of requirements. Running through the options systematically, as Maurice would have had to do during his development testing, would have eliminated dozens of candidate materials before arriving at the right grade of paraffin. Beeswax melts at the right temperature but leaves organic residue. Carnauba wax has too high a melting point. Synthetic waxes of the era had unpredictable combustion characteristics. The specific petroleum-derived paraffin that Maurice settled on was essentially the only material that met all the requirements simultaneously. Finding it required either extraordinary luck or systematic testing. Given what we know about how Maurice Petty approached engine development, systematic testing is the overwhelmingly more likely explanation. The dyno testing program that supported the wax engine development also tells us something important about the resources Petty Enterprises was willing to commit to this project. Dynamometer time is expensive. Engine components consumed during testing are expensive. The dedicated test cell they reportedly built for this specific program represents a significant capital investment for a racing team operating in 1983. This was not a casual experiment. It was a funded research and development program with specific goals, defined metrics, and iterative refinement based on measured results. By the standards of what most people imagine when they think about garage-level NASCAR cheating, it was remarkably sophisticated. The secrecy maintenance required to protect the program was itself a management challenge. Racing teams are not naturally secretive environments. They are small, tight-knit communities where information flows freely among people who trust each other. Keeping the wax program confidential while still conducting meaningful testing and race application required that every person involved understood the stakes and maintained discipline under conditions where a single careless conversation could expose everything. The fact that the secret held for as long as it apparently did speaks to the trust and discipline within the Petty organization at that time. Consider also the psychological dimension of running this scheme during actual races. Every pit stop was a potential exposure point. Every conversation with NASCAR officials required careful management. Every post-race celebration had to be conducted with the knowledge that the car rolling into victory lane was not the same car that had been inspected before the green flag. The crew members who knew had to maintain normal appearances, normal conversations, normal interactions with officials and media and rival teams, while carrying knowledge that could end careers and damage the sport's most iconic franchise. That kind of sustained performance under pressure is its own form of skill. The wax engine story also raises important questions about the nature of record books in motorsport. Richard Petty's 200 career victories stand as the all-time NASCAR record, a mark that has not been approached by any driver in the modern era. Dale Earnhardt reached 76 wins. Jeff Gordon reached 93. Jimmy Johnson reached 83. The gap between Petty's record and the next generation of great drivers is enormous, and various explanations have been offered for it, including the longer seasons of earlier eras, the different competitive structures, and the varying quality of competition across different periods of the sport's history. The wax engine, and whatever other technical advantages Petty Enterprises may have deployed during their dominant period, exists in the background of that record conversation, not as a definitive explanation, but as a complicating factor that honest historical analysis cannot completely ignore. Racing records are products of their era. They reflect the rules, the technology, the competition, and yes, the creative interpretation of regulations that characterize the time in which they were set. Understanding Richard Petty's record requires understanding the full context of how racing was conducted during his career, including the parts of that context that are uncomfortable to examine. The final chapter of the wax engine story isn't really about NASCAR at all. It's about what this incident reveals when you hold it up against the broader human experience of competition, creativity, and the eternal tension between rules and the people smart enough to find their limits. Because here's the thing about stories like this one. They endure not because of the scandal, not because of the penalty, not even because of the audacious technical cleverness at their center. They endure because they tap into something fundamental about how human beings respond to constraints. Give a genuinely creative mind a hard limit, and the first question that mind asks is not, how do I work within this limit? It's, where exactly does this limit actually exist? And what happens right at the edge of it? Maurice Petty asked that question about the 358 cubic inch limit, and found an answer that nobody else had seen. That finding process, that moment of insight where melting wax and cold inspection measurements connected into a coherent scheme inside his mind, represents the kind of lateral cognitive leap that innovation researchers study and try to replicate in controlled settings. You cannot teach someone to have that thought. You can create conditions where that thought becomes more likely. Deep domain expertise, so that you understand the problem space thoroughly enough to see its hidden dimensions. Genuine competitive pressure, so that the motivation to find unconventional solutions is real and urgent. Freedom, from the assumption that the obvious answer is the only answer. Maurice Petty had all three of those conditions in abundance. The domain expertise part is worth dwelling on, because it's easy to underestimate how much Maurice knew about engines by the time he developed the wax scheme. He had been building racing engines since the 1950s. He had personally constructed motors that powered his brother to 7 NASCAR championships. He had torn down and rebuilt thousands of engines, measuring every component, understanding every tolerance, developing an intuitive sense of how small changes in physical dimensions translated into meaningful changes in power output. When he looked at a combustion chamber, he didn't see a space. He saw volume, temperature, pressure, airflow, fuel atomization, flame propagation. He understood that space in multiple simultaneous dimensions. That depth of understanding is what allowed him to see the wax solution where nobody else saw anything. A casual observer looking at a combustion chamber sees a cavity machined into metal. Maurice Petty saw a volume that existed in physical reality, but only needed to exist in measured reality during the cold inspection window. Everything after that inspection window was a different problem, governed by different physics, subject to different constraints. The wax was the bridge between those two realities, and he could only build that bridge because he understood both realities with extraordinary precision. Here's what most people don't realize when they examine the technical details of what Maurice built. The hardest part of the wax engine program was not the chemistry or the material selection or even the precise installation procedure. The hardest part was the camshaft design. Remember that the camshaft controls the timing and duration of valve opening events, which determines how efficiently the engine breathes at different points in its power band. A camshaft ground for optimal performance at 358 cubic inches will not be optimal at 373 cubic inches, because the airflow dynamics, the cylinder filling characteristics, and the exhaust scavenging behavior are all meaningfully different at the larger displacement. Maurice had to design a single camshaft that would work adequately at 358 during inspection and warm-up, then perform optimally at 373 once the wax was gone. That's not a trivial engineering problem. It requires modeling the engine's breathing behavior across two different displacement states and finding a cam profile that represents the best available compromise between them. In 1983, without modern computational fluid dynamics tools or sophisticated engine simulation software, this work was done through physical testing, careful measurement, and the kind of accumulated intuitive understanding that only comes from decades of hands-on engine development. The dyno cell at Levelcross ran countless hours developing that cam profile, burning through engine after engine in the pursuit of the right answer. The exhaust system presented a similar challenge. Racing exhaust headers are tuned to specific displacement and RPM combinations. The primary pipe diameter and length, the collector design, the merge collector angle, all of these parameters interact with the engine's displacement and breathing characteristics to create scavenging effects that pull exhaust gases out of the cylinder more efficiently, which in turn helps draw the fresh intake charge in more effectively. Headers tuned for 358 cubic inches will generate different scavenging characteristics than headers tuned for 373. Maurice had to find header dimensions that worked across both configurations without being obviously suboptimal at either. The solution he arrived at reportedly split the difference, accepting slightly less than optimal scavenging at 358 during the early laps of a race in exchange for very good scavenging at 373 once the wax had melted. This meant that during qualifying, when the engine ran at 358 for the entire session, the car might not show its best possible lap time. A slight underperformance in qualifying was an acceptable cost for the race day advantage the system delivered. And in fact, a car that qualified respectably but not spectacularly, and then went on to dominate the race, would attract less suspicion than one that set the fastest qualifying time, and then somehow went even faster in the race itself. This is where the scheme shows its full sophistication. Maurice wasn't just engineering a faster engine, he was engineering a deception that managed its own visibility. The car behaved in a way that was suspicious only in retrospect, once you already knew what to look for. In real time, a team that qualified in the middle of the field and then found pace as the race went on was simply demonstrating good race setup. The ability to build a car that got better as the track rubbered in and competitors' tires wore down. That was a legitimate and respected competitive skill in 1983 NASCAR. The wax engine mimicked the outward appearance of that legitimate skill while achieving the result through entirely different means. The question of whether Richard Petty himself knew about the wax is one that racing historians have debated for decades without reaching a definitive conclusion. Richard has always maintained that he drove what Maurice built, and that his job was the car, not the engine. That's a carefully constructed answer that is technically true regardless of what Richard actually knew. Drivers in that era were deeply involved in their equipment in ways that modern drivers, who have entire engineering departments interpreting data between them and the car, are not. Richard Petty drove those engines for hundreds of laps in testing, felt how they behaved during warm-up, felt the power increase as temperatures climbed, experienced the exact moment when the engine seemed to come fully alive somewhere around lap 12 to 15. Whether he connected that experience to a deliberate mechanical scheme, or simply accepted it as the mysterious way Maurice's engines worked, is impossible to know from the outside. What seems clear is that he trusted Maurice completely, and that the trust was the foundation of their working relationship throughout their careers. If Maurice told Richard that the engine would get better as it warmed up, Richard would have accepted that as the natural behavior of a motor built to a particular specification. The technical details behind that behavior were Maurice's domain, and Richard respected those boundaries as clearly as Maurice respected the boundaries of the cockpit. The story of what happened to Petty Enterprises in the years following Richmond is in some ways the most poignant part of this entire narrative. The team that had dominated NASCAR through the late 1970s and early 1980s gradually declined in competitiveness through the middle and late part of the decade. Richard's 200th win at Daytona in 1984 proved to be nearly his last. He would win only once more after that, at Philadelphia in 1992. In a race that was itself later found to have involved engine irregularities. The King, who had seemed nearly unbeatable for more than a decade, became a beloved, but no longer competitive presence in the garage, a living monument to an era that was passing. Multiple explanations exist for that decline. The sport was changing, becoming more professional, better funded, more technically sophisticated across the board. Teams that had previously relied on individual genius were giving way to organizations that deployed systematic engineering processes. The advantage that any single innovative mind could create was shrinking as the collective technical level of the field rose. Richard himself was aging, past 50 by the late 1980s, still skilled but no longer possessing the reflexes and physical resilience of a younger driver. And Maurice's health was declining, limiting his ability to drive the engine development program with the same intensity he had brought to it throughout the previous decade. But it's also true that the loss of the technical advantages that had characterized the team's dominant period, whether the wax engine or other innovations that may never have been publicly identified, coincided with that decline in competitiveness. Correlation is not causation, but the timing is difficult to ignore entirely when you're trying to construct an honest picture of what drove the team's success during their best years. The lasting technical lesson from the wax engine program is about the relationship between simplicity and elegance in engineering solutions. The instinct in competitive engineering is often toward complexity, toward adding systems and components and mechanisms that create advantages through their sophistication. Maurice Petty went the other direction. He found an advantage in removing complexity, in using a material that would simply not exist anymore after it had served its purpose. The elegance of the solution is proportional to its simplicity. The fewer moving parts, the fewer failure modes. The fewer components, the fewer detection points. The simpler the mechanism, the harder it is to find because investigators are naturally drawn to look for sophisticated solutions to sophisticated problems. This principle, that the simplest solution to a complex constraint problem is often the most powerful one, appears repeatedly in the history of technical innovation across many fields. The best cryptographic attacks often exploit simple assumptions that complex systems make. The most successful business model innovations often involve removing steps from processes that everyone assumed were necessary. The most impactful engineering breakthroughs often come from questioning whether a component that everyone takes for granted actually needs to be there at all. Maurice Petty, working in a NASCAR engine shop in Levelcross, North Carolina, independently discovered and applied a principle that spans far beyond motorsport. What ultimately makes this story worth telling, worth examining in this level of detail, is not the scandal, or the penalty, or even the remarkable technical cleverness. It's the reminder that genuine innovation looks strange from the outside. It looks obvious in retrospect. It looks impossible right up until the moment someone does it. The people who knew Maurice Petty describe him as someone who thought about engines constantly, who would wake up in the middle of the night with an idea and go to the shop to test it immediately, who never accepted that the current state of knowledge represented the final word on what was possible. That quality of relentless, restless, creative engagement with a problem is the source of every genuine breakthrough in any field. The wax engine was illegal. It was a violation of NASCAR's rules, and the penalty that followed was appropriate and deserved. None of that changes the fact that conceiving it required a quality of mind that is genuinely rare and genuinely valuable. The same cognitive qualities that led Maurice Petty to paraffin wax and melting combustion chambers could have led, in a different context, to a legitimate engineering breakthrough that advanced the entire field. The difference between genius and cheating is sometimes nothing more than which side of a specific rule you happen to be working on. Today's NASCAR is a world away from the Richmond Fairgrounds in February 1983. Engines are sealed with tamper-evident devices between inspection and racing. Displacement is verified using multiple independent methods at multiple temperature points. Electronic monitoring systems track engine parameters in real time throughout every session. The era of the individual mechanical genius finding a loophole that the entire regulatory apparatus missed is effectively over, replaced by a system designed specifically to make such discoveries impossible. Whether that's entirely a good thing is a question worth sitting with. The regulatory sophistication that makes racing fairer and more equitable also makes it less hospitable to the kind of lateral creative thinking that produced the wax engine. The same system that prevents cheating also constrains genuine innovation, because genuine innovation and creative rule interpretation often emerge from the same cognitive place. NASCAR's modern engines are extraordinarily sophisticated machines, but they are sophisticated within very tight specifications. The freedom that allowed Maurice Petty to ask what if has been systematically eliminated in the name of competitive equity. Racing has gained fairness and lost romance in roughly equal measure. The wax engine story endures because it represents that lost romance at its most vivid. A time when one person with an unconventional idea could change the outcome of races. When the garage was still a place where individual creativity could outthink institutional regulation. When the gap between what was legal and what was possible was still wide enough for a clever mind to find something genuinely new inside it. Maurice Petty found something new inside that gap. He found it with wax, patience, and a willingness to ask a question nobody else had thought to ask. And for at least one season, probably more, he turned that question into victories at the highest level of American motorsport. The fact that it ended in a penalty and a rule change doesn't diminish what he accomplished. If anything, it confirms it. You only change the rules when someone has found something the rules didn't account for. Maurice Petty found something the rules didn't account for, and NASCAR spent the next decade making sure nobody ever would again. That is the true measure of how significant the wax engine really was. Not the $35,000 fine, not the 104 points. Not even the victory that stood in the record books despite everything. The true measure is that one man with a block of wax and a cold inspection process forced an entire sport to fundamentally rethink how it verified the fairness of competition. That's not a footnote. That's a legacy.